没声音，好，要等一下啦，要等一下。
哦
对，你可能先。
Actually, is there a chair?
I think we can have some chair. Here. Yeah.
8，你试看看。刚刚有了。
Here you.
Yeah, but how do I move it?
Okay, then here you move another page.
Oh, I see.
But if you come back, maybe there was some delay.
Okay. All right. Back to go for Okay.
有，我想有没有？他等下在这边讲。
我去拿水，这我帮你拿。
是上面它有上面有。
Yeah, when come back, maybe they have some delay, but we can.
它这个
I lost my.
他回去的时候，他回前页的时候，他会自己消失。
对啊，为什么会前页会消失呢？
Then if you come back, they were 2 minutes.
对，为什么往后会消失啊？就
对，往后的时候好像会有点小，他有时候需要往后。所以只是挖。你们有那个？
它里面有那种别的麦克风，你没有？
因为怕他有时候要扶在。就这可以。
好问题，好，我想好像是第一张的问题，后面的往后没关系。
哦，OK，你都
这第一张好像有问题。我测试看看。
在后。
Okay, so maybe put me on the first page, and then I will never go back.
I never go to the first page.
就是如果要第一页的话，我要特别回去再重开这个。
Because long time we go Thursday, okay. 所以你如果你看到再把再这边调，
好，
因为 S to
Yeah, okay.
这样子有点那个，
Yeah.
对，要往后啊，就是。对，他。
要试试看其他可以啊，试试看其他可以。
哦。
压抑。 So let me try. I think it is. They are standing one.
Yeah. I think.
Yeah, it's like a standing one. You don't need a hold.
Because if I hold,
I think you don't need. 就它有些是可以绑，它没有那种。不然你就帮他 hold。The worst case is Chini will help you. It's no problem. Yeah, it's still early. I will first introduce you.
hello, hello. Okay, okay. We got one. Yeah, we got one. We found finally.
Oh,
Great, thank you.
太感谢了，太感谢了。
Try. Miss. I think we.
或者说裤子
My
这
God.
个，
Okay.
可能放在裤子。
Yeah, on the
放
pocket.
在裤子。
Okay.
Yeah, put it in.
Pocket.
Okay, oh, great. That's great. Yeah, thank you.
So maybe you test a little bit.
No, no, I heard it.
Okay.
Yeah, thank you.
那个应该关起来，它会回音的。
Thank you.
OK。我在想说，椅子是不是要靠？
请各位嘉宾注意，演讲厅是禁止饮食的。
哦，所以它比较左，没有说是可以靠这边比较。
Turn the mic.
请大家注意，本演讲厅是内禁止饮食。Please note that no food or drinks are allowed in the lecture room.
下给你的重要任务。刚我跟仲明讲，他说问了他给他生日费，他没有开玩笑。对我压力。
大会主讲即将开始，请进处就座，并请您将手机关机或转震动，以免影响场内会议的进行。谢谢您的合作。The plenary talk will begin shortly. Please take your as soon as possible and to switch your cell phone to silence mode. Thank you for your cooperation. 各位贵宾，接下来是大会主讲时间，让我们欢迎主持人肖千玉老师。Next, we are moving into our plenary talk. It is my pleasure to introduce Professor Chen Yu Xiao, who will be chairing the session. Professor, please.
谢谢大家。Good morning, everyone. Welcome you all to today's talk. It's a great pleasure, great honor to introduce our speaker today, Professor Feng from Columbia University. So Professor Feng is a towering figure in the world of mathematics. He is a world-renowned mathematician whose work spans geometry analysis, complex geometry, and the string theory. Professor Feng is one of the few mathematicians who possesses masterful command over both linear and nonlinear degrees. In this both of these formidable fields, Professor Feng conducted foundational and groundbreaking work from his classical on this singular Schrödinger operators, singular Ledon transform, to his very deep pioneering work in multiple equation, stability in complex geometry, and the string theory. Okay. So now, Professor Feng, his work has not only solved long-standing problems, but also laid very groundwork for generations. So today, we are privileged to hear from him about this Taylor geometry and the complex equation. So please join me in welcome Professor Feng.
Okay. Thank you. Hey, no, here, sir. Yeah, okay. No, he keeps.
You have this one. It's okay. Yeah, it's okay.
Thank you. Well, first I would like to say how happy and honored I am to have been invited to give a talk at this annual meeting of the Taiwan Math Society. It's really a great honor and great pleasure to be here. And I'm very grateful to the warm hospitality which I have received from everyone who also cheerfully put up with my present handicap coming from a disease I'm recovering from. So again, my thanks to you all. So today I would like to talk about the title says here, Kähler geometry and the motion pair equation. So let me begin by a few words of introduction. Here maybe. Oh, the other direction. Yeah. Okay. Right. So, Kähler geometry is a particularly important area in mathematics, which because it's at the intersection of three different fields, all of which are major fields, namely differential geometry, algebraic geometry, and partial differential equations. So some early landmark results are the Kodaira theory of harmonic forms and the famous Kodaira embedding theorem. And those were based on the theory of linear elliptic partial differential equations. A newer area coming after these developments with very wide ramifications in geometry and physics was ushered in with the Calabi conjecture in the 1950s. This Calabi conjecture addressed the existence of flat scalar metric, and its solution by S.T. Yao was a real landmark. And the analytic tool is now no longer linear elliptic PDEs, but linear elliptic PDEs. So, but more recently, an analytic theory building on Yao's theorem can also go much further and accumulate a wealth of, one may say, unexpected geometric information for Kähler manifolds, including diameter and volume estimates, Green's functions, Sobolev inequality, and improved version of the Gromov convergence theorem. The remarkable thing about all of these is that these results are much stronger than the Riemannian analogs. So Kähler has these amazing properties that were rather unexpected. So in this talk, I would like to survey some of the developments. We have to cover a lot of ground, right? So the discussion will be a little bit impressionistic, but please just put up with it, you know. One does have to go through every detail. Okay, so let me now describe what's the plan of the talk. So first of all, I would like to describe the Kähler condition. It's very simple, but it's good to know how it arises. And one way it arises is by guaranteeing an equality between the Kern connection, which is from compact geometry, and Levi-Civita connection, which comes from Riemannian geometry. So for these to coincide, one has to impose the Kähler condition. So it's a condition that says that the complex structures, the Riemannian structures are compatible. Then the next thing is that here is the most important consequence, is that although one can write down the Kähler conditions as just a simple identity, the key thing is that it has some very simple but very important cohomological consequences. So I will describe those, and then the moment we have this, and we have another tool called the Didi-Bar lemma, which I will also explain, then you will see that invariably, inevitably, what we say, the moment you have a Kähler matrix, they are characterized by a Monge-Ampère equation. So Monge-Ampère equation, I go back to that a little bit later, partial differential equations of second order, whose leading term is the product, the determinant of the unknown function. So this is the background, and then I will describe the Calabi conjecture and some key ingredients of Yao's solution. Now all of this date from the Calabi conjecture is from the mid-50s, and Yao's solution is from the mid-70s, and now we jump to the present day. Right? And I would like to describe to you a kind of fundamental current issue in geometry nowadays, which is the pre-compactness of families of manifolds. So this has to do, I'll explain the motivation later, but essentially, as we are all aware of, right, in real analysis, we have the Ascoli theorem, right, which tells us when a family of functions would have convergent subsequence. Now, in modern days, we have to deal with something a little bit more complicated. We don't deal with families of functions, but we deal with families of manifolds. And the question is that if we have a family of manifolds, when does it have a convergent subsequence? Now, it turns out that, as I will describe in greater detail later, is that in order to have a convergent subsequence of families of manifolds, at least when these manifolds are Riemannian, then one typically has to impose the condition that they have a uniform upper diameter bounds and uniform lower Ritchie bounds. I describe that in detail later. And precisely these are very hard to obtain. So due to that, it's very hard to obtain conversion subsequence. And now the recent discovery in Keller geometry, recent in the sense that it's only 4 or 5 years old, is that when we deal with Keller metrics, then it turns out that we're going to have a much better estimate, really robust. And these estimates will bypass these difficulties. And as a consequence, one can prove many theorems on plate compactness that one did not expect before. Now, how did this come about? I will describe not the proof in detail, but three key ideas which I think will be recurrent in the possible future. The first is that once again, right, we have to make use of the fact that Keller implies immediately Montgempaire, and then the key new ingredient is that we should focus on the Green's function for these manifolds. And normally, to say that we focus on the Green's functions is not of much help, because how do we, find out information about it? And here comes a new idea, which is that Green's functions can be estimated in a very sharp manner using a method of auxiliary equation, which is that if you want to solve a PDE, it suffices for you to construct an auxiliary equation, which is a Montgempaire equation, and the existence of solutions to that equation is guaranteed by Young's theorem. And then knowing this, there's a method for how to extract information from that. So that's how that goes. And if we have time, I will describe to you one of the directions where progress can be, has also been found, which is that these arguments are so robust that they also extend to singular Keller spaces. Now, the issue of singular Keller spaces is not a mere attempt at being very general. It's just that if you want to apply differential geometry to algebraic geometry, you have to deal typically with singular spaces, because the solutions of typically a polynomial equation is not defined as smooth variety. That variety will have singularities. So this is what I would like to describe. And again, the discussion may be a little bit pessimistic, but hopefully you put up with it. Okay? So let us begin with the Keller proposition. So actually, before that, I have to explain about the complex manifold, which is a notion which I assume most people are familiar with, but let me at least set up the notation. So first, a complex manifold is a topological space which can be covered by coordinate charts. So X, the union of mu, X mu, and now these are charts in the sense that each of them is in one-to-one correspondence with the open set in Cn, if this is an n-dimensional space. And in this correspondence then, if we take this chart X mu and we take a point there, then corresponding to this point is its coordinates in Cn. So let me write a Z mu like this. It's a lot of indices, but this is of course an n-dimensional vector. So it has components Zj, where J runs from 1 to n, and I put a subindex mu when we deal with the chart P mu. So this is our local coordinate for this chart. And now suppose that we are in the intersection of two charts, X mu and X nu. In that case, you see then that you have a luxury, because you can either use the coordinates Zj mu associated with X mu, or you can use the coordinates Zk mu, which are associated with the chart X nu. And the key thing is that it should not make any difference which coordinates you choose. And in practice, it suffices that can be guaranteed simply by requiring that when you view one set of coordinates as a functions of the other set, then these functions are holomorphic, and furthermore, they are Jacobian, is invertible. So this is a simple condition that tells you that whatever what you can do in these coordinates by using this, you can also do in these coordinates. So now just as a detail for perhaps the students who haven't seen functions as yet of several complex variables, let me just say that things are very nice here. If you have a function of several complex variables, like in here, this thing here is a function of those, then it's holomorphic if it is holomorphic in each variable. So this is even simpler than differentiable function. And so, as I have mentioned, that so this simply means that one can go from one chart to the other. So let's not, so we don't worry too much on which chart we work on. So when that happens, and we don't care which chart we work on, we will just drop this index mu, which reminds us of which chart we are on. And dropping the index mu, things clean up a little. Okay. All right. So this is our complex manifold, and now let's deal with the notion of Kähler method. So let me begin by telling you the basics about connections and curvature in complex geometry. So it's actually extremely simple, right? Now what happens is that our manifold X is a complex manifold. So now normally on a standard smooth manifold, we have smooth vector fields and so on. But in a complex manifold, we still have that. But the advantage is that complex vector fields can be decomposed into 1, 0 component and 0, 1 component. So here it is. This is our vector field. And you see that this is one set of components that has the feature that it involves the derivative in the z variables. And this is the other set, which is characterized by that it involves the z bar variables. And I put here Vj and here V tilde, not the conjugate. These are different. Now, if we go to different coordinate chart, then we can express it in the same way, right? With the different sets of coefficients, and with the coordinates now instead of z mu k, is now z mu k. So how are these related? Well, it's very simple, right? It's just a chain rule, right? So because of this nice splitting, right? There is no mixing. So when they transform, this thing here transforms into that, this thing here transforms into that. So that means if you compare this and that, then by the chain rule, you find that these coordinates V new here are given by these coordinates V new here, and then by the Jacobian of the transformation of Vj. So and then similarly, of course, for the C bar. So what we have, right? Because we have a complex manifold, is precisely the splitting that in some sense reduces our discussion to half the number of variables. Now, I want to stress that by definition of the complex manifold, these transition functions here, this one here is holomorphic, and this one here is anti-holomorphic. Now, so let's now try to differentiate, because so what happens is that we know that locally our complex manifold is given by a chart. Let's look exactly like Cn, so we can use the standard derivatives of Cn. But the key thing is that we rule them back, right, and have something well defined. And you see that in general there's some trouble. But when we deal with a complex manifold, let me point out that one can always differentiate in the bar direction without any trouble. Because if I take these components, let's say Vm, right, and then I differentiate in the bar direction, then the bar direction will go right through these transitions. So they don't create annoying additional terms that destroy the transformation rule. So that means that on a complex manifold, we can define not all derivatives, but at least the bar derivative. And similarly, if we can differentiate in the unbar directions, but only the ones that transform with an anti-holomorphic transition. So next lesson that we learn, right, one can differentiate, but only in half the number of directions. Not all. Now, so now we have to deal with this difficulty. We cannot do analysis with only half the derivatives. We have to deal with them more. So that means that we have to put additional structures. Right? So what kind of additional structures can we put? We can put a metric. So this is what I wrote here. So let's say, what is a metric? A metric is something that is a quadratic form gk by j, thanks to which we can define the length square of a vector field. So you see here that having a gk by j here, which we can think of as a matrix, then we can define the length square of V as gk by j, vk by vj. All right. And let me introduce the inverse matrix. So the inverse matrix is the one which is it's characterized by, again, the same letter G, but this time the indices are written up instead of that. Right? And the fact that it's inverse means that when you multiply the inverse matrix by the metric itself, then you should get the identity in the connector delta. So having this gk by j here, I introduced this inverse matrix, and now I claim that there is now, having such a metric, there is a very simple way for me to obtain a notion of derivative in the unbar direction, which is guaranteed to transform well. How? It's very simple. Here's the formula. You see, it's very simple because the way you should think of this formula is this. Our vector field has upper components VQ, let's say. Now, when you contract, when you lower this Q index with the Hermitian matrix GK by J, notice that the Q indices get contracted, and so they disappear. So what's left is something that has only a bar in the index. But if it has a bar index, it transforms with anti-holomorphic transition function. But if it transforms with an anti-holomorphic transition function, then the EJ derivative goes right through it. This is well defined, and now you contract back the bar, and that is it. So this is guaranteed to produce something covariant, and we can write it down more explicitly. If we apply the Leibniz rule to this, if DJ less than K, it gives you DJ VM, and then these two here cancel and become the identity, so that gives you that first term. Or else DJ length GR by K, and so that produces a new term here. So here you see that DJ has landed on GR by Q, and then you have GM. Right. So the net effect of this prescription is that we have gotten a new covariant derivative guaranteed to transform well, and it differs from the naive one that does not transform well by adding this term, which is called the correction term. Now, so here are the way we define connection in complex geometry equipped with the metric. Now, for having this, it's easy to derive what are the curvature and torsion. So let's call this a Chern connection, and a very simple calculation tells you the following. So what is the curvature? The curvature is very easily understood in this language. What it is that having introduced a covariant derivative in the bar and an unbar direction, they are guaranteed to transform covariantly, but the price that we pay is that they no longer commute. So the measure of how much they don't commute is called the curvature. So more precisely, we write the bracket delta J by VM, and so it's not zero. And you see that what is it? It has to be something that has to have indices K bar and J, And then since it acts on this vector field here, it has. So it automatically is a complicated object that has a 4 in it. And here's the formula. So this is the curvature tensor, right? And then the torsion, as you know, is defined by you take the connection, right? And then you anti-symmetrize. So here is AMJQ, anti-symmetrize Q given J, and that's the torsion. So we do that, then you see we can factor our GM and this is the anti. And now we learn immediately something, which is that this, although this is very natural, it's not the same as a connection that we are very familiar with in Riemannian geometry. Because in Riemannian geometry, there's a natural connection in presence of a metric called the Levi-Civita connection, and its characterizing feature, its torsion is 0. And now you see our Chern connection, here is its torsion, which may not be 0. So the 1K where it is also 0, simply we define that to be Kähler matrix. So Kähler matrix are precisely metric for which the Chern connection has 0 torsion and coincide with the connection. So Kähler matrix are matrix for which a complex structure and a Riemannian structure coincide and happen. And now, if we have that, let me also point out the following. In geometry, right, people are aware of the fact that in higher dimension, the curvature tensor has all these components. That's very difficult. So one can imagine considering at least as an intermediate notions that are a little bit simpler. So one way of one simpler notion is the so-called Ricci curvature. So the Ricci curvature is obtained by taking the full curvature and taking the stress. So that means that we want to contract the indices M and Q. So we obtain here R, K bar J, M, N, places like this. And then we find something remarkable, right? Let's look here at this formula, R, K bar J, M, Q. And suppose that we take the trace, meaning the M is equal to Q, and we act. So we obtain that minus dk bar, G, M, Q bar, G, R bar, G, Q bar M. And now you recognize that this thing here is actually the dj of the log of the determinant. Because the way you compute the log of a matrix, you get precisely the trace of the matrix inverse times dj times the matrix. So this simple prescription of taking the trace that gives you the Ricci curvature also tells you that the Ricci curvature, at least in complex geometry, has this following remarkable expression. It's minus dj dk bar of the log of the determinant of. So that's what we have learned by some very simple consideration. Now, why is this so important? Well, we are going to see it immediately. So far, I have defined the Kähler condition as some kind of identity, but we wanted to make the torsion disappear. But actually, there's some cohomological consequences which are very important. I'm describing. So let's take a metric, and given that metric, let me define the Kähler form as if I have metric k by k. I define the Kähler form as gk by j, dj, y, dz by k. So this is now a 1-1 form, and it takes one line calculation to verify that the Kähler condition had introduced by an explicit formula in the previous page is equivalent to simply this form here being closed. Now this is great because the moment that the form is closed, we can associate to it its Ram cohomology class. So to a Kähler metric, there's a cohomology class called its Kähler class. And now, in a given Kähler class, you can ask how do two metrics in a given Kähler class differ? Well, the DD bar lemma tells you the complete answer. Suppose that you have a compact scalar manifold, then the key statement is that if you have an exact 1-1 form, then actually you can write it as dd bar of something. So this is, you see again a derivative, because if you write psi as an exact 1-1 form, you give the psi is equal to d something, right? So that's the one derivative. But to write psi as dd bar of something, that's two derivatives. So in particular, suppose that you have a two scalar matrix, omega 0 and omega, in the same scalar class, then the difference, right, is an exact 1-1 form and can be written as I dd bar phi. So this means that the moment you have chosen your scalar class, and the moment you have fixed a reference form, your scalar metric is characterized by a scalar function. Nothing complicated, no longer anything complicated, but just a scalar function. And the scalar function is unique up to an additive function. Now, let me now show that we are now that now we have a Mohr-Ampere equation. Let me begin by reminding you of what is the volume form. In general, if you have a metric, volume form is simply the determinant of the metric. But in complex geometry, there's a simple way of writing that, because instead of thinking about the determinant of the metric times the product of the canonical forms, I can simply take this scalar form omega and raise it to the power omega n to the power n. See that if I take this and then raise it to the power n, I'm multiplying it with itself n times. And so I group together all of these things, that's going to give me this factor. And then for the others, but then to put the product of all of these into this form, I have to do some rearranging, some plus minus sign, and that rearranging, the moment's thought, you can recognize as the product of this term here together with signs that make it a determinant. So, so what happens then is that our it's just equal to omega n, right? Omega to the power n. So let me introduce the potential K omega, and so given a metric omega, this is it. And now this is the topology, right? We have a metric omega, we raise the power n, we call it the volume form. What have we learned from that? Well, actually, what we have here is a Mohr-Ampere equation. Because what happens here is that, look at this equation. Omega n is equal to u omega, but omega n, by definition, is omega to the power n, and omega itself is omega plus I dd bar phi. So raised to the power n, this is what I have, right? So this is a complete topology, right? However, right, suppose that we fix omega 0, and suppose that our Hermitian metric omega, omega, we know its volume form. So if that's the case, then in this equation here, omega 0 is known, volume form is known. So this is an equation for phi, and this is precisely a Mohr-Ampere equation. It involves two partial derivatives of phi and the so you see that the appearance of a Mohr-Ampere equation is not so it's just a scalar condition together with the dd bar lemma. But, how it's amazing how far one can go with this. So try to describe that. So introduction is this is the Calabi conjecture and Yao theorem. Right? So let's start from something which is very, very basic, 19th century math. Right? So that's the uniformization theorem, and it can be formulated in many different ways. But the key thing is that it classifies compact surfaces by the existence of metric with constant curvature. So that's one of the formulations of the uniformization theorem. And in particular, among these compact surfaces, the torus, right, most the fundamental Riemann surface carries a metric with zero curvature. Now let's try. So this is only in one dimension. This is a Riemann surface, not convex dimension. Now what happens in higher dimensions? Well, you can see already from the previous discussion that the situation is going to be more thorough, because in the previous uniformization theorem, you needed only this impose a curvature condition, but this is more thorough because now our curvature is very complicated. It has a four sets of indices. So what should we impose? Right. So there are several notions of curvature, and which one should we use? Well, the naive thing is this: if we are looking for a metric, right, it's natural to consider to impose some condition of curvature, which is also a 1-1 form, because a metric is a 1-1 form. So if you impose the condition which is a 1-1 form, the number of equations is match the number of 1 form. So this is a naive condition, and now we can ask, what is a notion of curvature which is a 1-1 form? Well, this is, I dare not turn back, because I may not be able to get back to it. But just in the preceding slide, right, we define the notion that we call the Ricci curvature, and the Ricci curvature actually is a 1-1 form. Right? So it's natural then to try to develop a uniformization theorem based on the Ricci curvature. So let's try to understand this a little bit better. So remember, we have already defined this the Ricci tensor, right? And now we define the Ricci form by simply taking the 1-1 form whose coefficients are the Ricci tensor. So remember also the formula that I derived last time in the previous slide. That Rk by J is dj dk bar of the log of the volume. So if I write it like this, then that is simply Ricci omega minus I dd bar of log omega. But here it's trivial. If you look at this is a closed form, because I can replace partial d here with the full d, because d bar by d bar square is 0. So for this formulation, I see immediately that the Ricci form is closed form. And now I want to look at the cohomology class. I claim that although the Ricci is a closed form, it's the Lamb cohomology class is independent of the particular metric. If I have metrics of omega tilde, I can look at the difference of their Ricci forms, and this formula is d bar the log of the ratio, but the ratio of two forms is a scalar. So this is the exact form. So therefore, these two are homologically equivalent. So the Ricci form is independent of the cohomology class. So it's an invariant of the class itself, and we call that the first class. All right. So we are in. So how can we put this to good use? Well, so remember that I was trying to find uniformization theorem. So the first thing for me would be to try to look for the analog of the torus in 0 dimension, and I can view the analog of the torus in 0 dimension as those manifolds that carry a metric that satisfy the Ricci flat condition, like this curvature condition. Now, this equation is very attractive because besides being a natural generalization of elliptic terms in complex geometry, it's also analogous to Einstein's equation. So let's try to solve this. Well, you see then that to solve this, let's find the SI condition first. Then it suffices to take the cohomology class of both sides. Cohomology class of Rk by J class. You see that this SI condition is that C1 of X is equal to 0. So this is not so difficult to see, right? But the contrast is a very good conjecture of Calabi-Yau time. Right? So Calabi conjecture is true. If you take a compact Kähler manifold that satisfies this, then for any Kähler class, exactly one Kähler matrix satisfies. So not only such a matrix abundant, right? You exist, they are abundant. You can have any Kähler class as long as this condition holds, which is in high the demand surface being a torus. And so this was in the mid-50s, and complex geometry is the following theorem of Yau, right? The Calabi conjecture is true. So this has an amazing number of consequences, which I don't have time to go into. But what I would like to study a little bit is that how did Yao prove this, and and why, and and uh, and, uh, and how relevant that is to our current goal of uh, in complex geometry. Okay, so so let me, perhaps I'm running a bit out of time. I'm just repeating here that this is the equation that one has to solve, and that if you want to solve RK by J, then actually the volume form is completely very simple, and therefore I think this thing is completely determined like that. We arrive at the equation like this, and this is the equation we solved. Right? So let me skip a little bit the detail here, and let me say his proof. So the proof of Yao is by the oops, sorry. The proof of Yao is by the method of continuity. And in continuity, what happens is that you want to solve some equation, and you try to pick an equation you know how to solve, and you try to connect the two, and then you go gradually from the one you know how to solve to the other. And then so every time you know how to solve it, so hope to solve a nearby points of the right by an implicit function theorem. That's not so difficult. Usually that's the hard part is this. You can imagine as you go along the path of the equations you know how to solve, as you move along that path, right, you may get stuck. You may not go beyond the solution. Right. Now to make sure that you don't get stuck, you need some estimate. That's the whole role of a priori estimates in PDE. And Yao proves the following. That suppose you take the motion pair equation, then you can estimate its zero norm by zero solution by a constant that depends only on the LQ norm of the right-hand side. This is the volume form to the in the LQ norm for Q strictly bigger than N. And then one can also estimate Laplacian of the solution. One can estimate the mixed partial of order 3. And having this, it's not difficult to deduce that if the right-hand side moves, then you can estimate the any norm of the solution, and that's enough to solve the Calabi conjecture. Now, I want to say that in order to describe a little bit how this falls short of our goal. The reason why this falls short of our goal is the following. As I mentioned at the beginning, nowadays we want to deal with families of manifolds. That means families of methods. But then you see then that although these bounds here, right, are independent of a lot of things, I did stress that they do depend on this reference metric omega 0. So as this metric omega 0 may vary and may degenerate, all these bounds. So this is right off the bat. That's one of the failures of the testing. A second thing, which is a little bit more difficult to explain, is that we are used to thinking about CK as ideal and fit in any use we have for our equation. But actually, they are all equivalent if you have all of them. But it turns out that in practice, that you don't have information on all the derivatives of the right. So due to that, you don't have information on all the derivatives of your solution. But rather, you want to be able to estimate still not in terms of the secant norms, but rather in terms of geometric invariance of your manifold, such as the. Okay, so let me try to be more precise. Now we come to the current thing in complex geometry. So as I explained before, so what happens? Right. So the major current theme nowadays is that whenever you have any kind of geometric structure, try to characterize it by a canonical matrix. And how do you find this canonical matrix? For example, an example of that is that for the uniformization theorem, you characterize the complex structure by a metric of constant scalar temperature. So this is more general, right? We want to characterize structures by canonical metrics. And how do we find them? Well, one way to find them is to try to form a metric, right? And just form it as a natural flow. And then we hope that the flow will converge to the metric that we want. A very famous example of that, of course, is the Poincaré conjecture, right? Where one deforms the metric of the round metric. Now, so suppose we have a geometric flow, right? That means that starting with manifold and symmetric, you actually end up with a whole path of manifolds together with a path of matrix. And now the question then is that does this path have some limit? So if there's a subsequence that has a limit, we can hope for that either this limit is already the canonical metric that we want, or else if it is not, we hope that we can continue the flow on the limit. So without going into detail, you see that the moral of the story is that we want to find our canonical metric by flow, and we want that flow to have some limit so that we can work with the limit. So that's why we did an Ascoli theorem for the sequential compactness of families of manifolds instead of functions. And now, are there such theorems? So there's a basic theorem that is due to a complex theorem due to Gromov. And the Riemannian version of this is the following. So the Gromov theorem tells you this, that suppose that you have a sequence of complex Riemannian manifolds, then the sequence admits some limit point if it admits a uniform lower bound on the Ricci, which is a uniform upper bound on the dimension. So if you have these two things, then you have a convergence. So, but now the catch is this: how often do we? It turns out that for many geometric flows, especially for any which is interesting, it's very hard to say either one or both. So this is the key difficulty that we have to overcome. So the claim that I would like to make is that these can be overcome in Kähler geometry. So here I'm describing the theorems in somewhat, of course, in detail, but since I'm running out of time, let me just sketch without looking at exact expression at the key features. So suppose we take an n-dimensional Kähler manifold and we fix a reference metric omega x. Then for each metric, let K denote all metrics. And and K, let me define the corresponding top volume. Right? So exactly the volume of omega n normalized by omega n, so that we have a scalar function, and we want to define here. So now, given that, let me define, and for each, let me define Nash Yau entropy to be given by, right? So you see that these some integral, right, of a function that characterizes the building block. But it's an integral, right? And then we can define the following set of scalar. Uh, Let me define this fixed n the dimension, uh, here which I fixed, and then let me define this set as the one whose dash the Kähler matrix, whose dash entropy is bounded by k, and whose intersection number, which is another integral omega x is bounded by. So let me define these sets, and now the claim is that we are going to have all the very compactness terms that we want for these sets. So this is a joint work with Jan Song and Jacob Sturm, and the bottom line is that if we have this set here which I described, then it is very compact in the sense of growth, and the limit is a compact matrix space. Now, so this is a this is a Kähler version, the Gromov compactness theorem. And it is very powerful because unlike the original Gromov compactness theorem, this Kähler version applies to matrix in here where you don't see any condition on the diameter and on the Ricci. You only have conditions on the intersection number and on the Nash entropy. So it's like you're getting two derivatives, right? And let me not go to this. This is how solve some long-standing questions on the Kähler-Ricci flow. Let me see, and let me also go. And let me also say that in fact, it goes even farther because one can obtain for these types of, for these parameters completely uniform Sobolev inequality. So, as you know, many here we are going, but if you have a Sobolev inequality, you can do things in geometry. This one, you know, it's there is such a thing in here. And let me also mention that we can even expand to normal Kähler spaces. So I don't have no question to here. So let me just say, I'm pretty close to running out of time. So let me just say that there are the three basic ingredients that Hermitian matrix are characterized by Moser pair equation. And the punchline is that the way to attack geometric estimate is to notice that they can all be obtained from the Green's function. The Green's function is defined by these formulas, and here you can give a simple argument by which the diameter is bounded by the L1 of the Green's function. If you have the L1 function, you are, and similarly for any others. Well, so, and now let me say that how easy is it to get the Green's function? Well, the Riemannian geometry is hopeless because the classic estimate of Chang Li tells you to estimate the Green's functions, you need precisely a lower bound for the Ricci curvature and estimate the diameter bound. Precisely the two invariants one estimate. So we would run into a vicious circle, but luckily, for Kähler matrix, right, there is a method which was introduced by Tong and I that gives proof of homology Sharp estimate. I don't have time to go into that, but the key thing is that this thing here, this method that we discover, can go farther and apply to all kinds of equations. One equation, surprisingly, is just a Laplacian, although that equation is different. So that's how we proved it. So I think I'm running out of time. So I'm forced to skip the rest. This I presume will be in the online, and those of you who are interested can take a look, right? And here I'm describing how that works, hit the equation and so on. And thank you.
So thank you very much for a beautiful talk. Please.
Yeah, thanks, Professor Fong, for his wonderful talk. So I have a question. So here, you improved the small degeneration consumption. For the estimate, you improved the small degeneration.
I cannot hear.
For the estimate, you improved consumption. Remove that
I am
condition.
going to more-
Can you that because it's
Well, it's a long story, but before, right, we had to redefine these classes, the W, P, and K, impose a condition that the volume form of these classes now is uniform below by a function whose zero set is at least the four-dimension too. Right? So we of course had in mind the fact that apply this to complex geometry. So any zero set is variety. So it automatically has four-dimension too. So in all our applications, it's automatically itself. But it turned out later, right, as I wrote down, the one group of VU, right? Notice the parameters estimated without that. And the other group is the Get and Toe, who were also doing for the green spectrum. And we also found a different proof that eliminated. So that's why nowadays, when we describe families of Kähler matrix, we don't have to mention this condition.
I see. Thank you.
Okay.
Thank you.
More question?
Thanks for the very nice talk. So I do have a question regarding the Sobolev inequality, which you obtained. It's the inequality here, this exponent Q. Based on my knowledge,
I tried to turn it back. Yeah.
yeah. So this Q, based on my knowledge, we can still not get the
No, right. In fact, so this is it. The applications, right? All we need is a Q bigger than 1, right? So that we are getting over L2 norms. Right? All we need. But now you can ask, indeed, how also what Q is in the case of Euclidean space. But and now one can show from our argument that you can take Q as close as you wish to the Euclidean value, right? If you make the conditions on this stronger, right? So, for example, here I just took some P, right, greater than N, but if I took P bigger and bigger, then I can improve on the this Q. But I'm not sure whether that's useful. The key thing is that notice that the moment you satisfy yourself Q bigger than 1, you get a completely uniform equality. Right? The analog of Sobolev constant is now completely.
Thanks. And I do have one more question regarding the space topic. Do we expect some nicer structures for boundary, like what Sun did?
Well, this space is defined by this, right? So in general, of course, you can have the omegas, the classes can be generated. that's the most interesting case.
We don't know any kind of structures here for the
No, not yet. No, that's a somebody was.
Okay.
Oh, okay. So, okay.
Any meaningful geometry meaning the constant here, and is this constant
Well,
base constant?
this constant here. Well, no, actually not. That's the point. Normally, you have Sobolev constant that depends in a very complicated way on the underlying variable, right? But here, you see here is completely, there's no geometry here, except for that depends and the dimension P, the thing that we use to define inertial entropy, K, what we use with Q. So C has no geometry, and all you have is I omega, which is the intersection number, and V omega, which is the volume. That's the marvelous thing about this, right? Instead of having right, Sobolev constants, they usually very complicated way on the underlying. But in these classes, you have absolutely nothing. The best, well, I think that. Oops, sorry. I think that the one space where one can improve is perhaps Q, right? Right now, we only know that Q is bigger than 1. Right? So one can perhaps try to improve the Q. But except for that, this form here is, after all, completely, general. Right? So I don't think you can improve this concept.
So any question? Further questions? Okay.
Thank you for a wonderful talk. Could you please comment a little bit more about how it extends the Sobolev inequality to the normal?
Okay, now this is a long story. I'm not sure the audience is going to see through it. But essentially, what happens in the normal case, you have to define the correct, you have to define the correct analog of the cases, right? So to define the correct analogs, right, you have to, which space do we have? We have to deal with a normal Kähler space, and now we have to pick a smooth resolution, right? And so we fix such a smooth resolution, the Kähler metric on it, and then we define the analog like this, which is the analog of this W with two additional conditions. Namely, a lower volume and the condition of the volume ratio, right? It has similarities, but with type analytics similarity, right? So one only deal with those, and for those, then what happens? Okay.
Okay, good.
So you obtained the results for this class W and K.
Yeah.
Is there a slightly larger class? Expect the results that you would like to because of some physical hypotheses, but you can't prove for technical reasons. So some enlargement of the class that would be interesting.
I don't expect a bigger class for which these theorems.
Like for example, you have the result for P strictly bigger than 1.
Yeah, I mean the type of class, right? How far up or down can one push P? That is a little bit unclear as of the moment. So, for example, the one kind of things which some people have already pursued is right. So instead of dealing with inertial entropy like this, right, which is defined by L log P, L log P, Orlick's law, right? Some people are beginning to introduce log of log. You, all right. So there's so one also define such a thing, and I think this term should hold. So you could try to go into more refined norms than this one. But the basic idea, I don't think can be improved. One has to improve. One has to improve some condition on the on the on the on the on the norm, mixed norm, and one has to impose some condition on the intersection number. And these are the only two we impose. So from there, I think. Yeah.
Thank you.
Any question? Okay, if not, let's thank the speaker again. Okay, thank you very much.
Oh, thanks. Yeah, let me.
Okay.
Yeah. Thank you.
延10分钟。那个我把上午的时间往后延10分钟哦。那中午午餐时间会缩短一下，所以我们等一下10:20再开始那个 payroll section。Okay. We'll delay 10 minutes, so the payroll section will begin at 10:20. Okay. The lunch time will be shorter. Okay. Okay. So our payroll section will start at 10:20. We have a tea break outside.
Thank you. Okay. I need to sit down.
Many people ask
Oh, I'm glad you like it. I'm sorry, I have to. Oh, I have to cut. Yeah. Yeah, okay.